Hello and welcome to chapter 21 on the quantum nature of light. This is going to be our chapter on quantum mechanics, as much as we're going to get into it. Actually, that's a lie. We are going to get into the atomic nature of, or the atomic model. So that is going to deal with quantum mechanics, but this is our introduction to quantum mechanics. And It focuses on light, but the thing to notice about this is, or the thing to note about this is that both it's true about light and it also happens to be true about matter. Most of what we say is true about both. So there's only a few slides of this because it's more intriguing uh, than at a very fundamental level or a very basic level of what we're doing, uh, we're not going to get through a ton of math on how to do this or anything like that, but we are going to talk about some of the properties and implications of this. So, first thing that comes out is that black body relationship, black body radiation, is a property of thermodynamics, which really gives birth to quantum mechanics in a real way, in the same way that electromagnetism gave birth to relativity, black body radiation and thermodynamics gave birth to uh, quantum mechanics. So what a black body is a black body is something that absorbs and re-emits all radiated energy that is incident upon it. And what we were seeing when we looked at black bodies, which is basically just a star. A star is a good example of a black body. Is that you were seeing these distributions of intensity versus wavelength for different temperatures. So 3000 Kelvin, 4000 Kelvin, and 5000 Kelvin are given in this diagram. So 5000 Kelvin is around the temperature of the sun. And what that means is that if you if the sun absorbs and re-emits all radiated energy, then looking at this graph, looking at this diagram, we see that it peaks right in the middle of the visible spectrum. So most of the intensity of the sun is in the middle of the visible spectrum, which is why we are able, or why our eyes can see it, or our eyes decide that that was a good area of this electromagnetic spectrum to look at. But it has this quality where it starts out with no, it starts out with no electromagnetic radiation emitted, and then it goes up, and then it goes down. So if you follow the 5000 Kelvin curve, the 4000 Kelvin curve, or the 3000 Kelvin curve, that's all true. It just depends on how intense it is. The sharpness of the peak depends on the temperature, and where the peak is also depends on the temperature. So something that's cooler is going to have a peak at a longer wavelength, which means that it has a lower energy, because remember that velocity was always equal to lambda f. So as lambda goes up, frequency goes down. As wavelength goes up, frequency goes down. So something with a lower energy temperature is going to have a lower frequency but a longer wavelength. But this is important, but this isn't what caused there to be quantum mechanics. What caused there to be quantum mechanics was something called the ultraviolet catastrophe, where classical theory would, instead of having this peak at 5,000 Kelvin, we had this green, or this peak at any temperature, but for 5,000 Kelvin, we had this green shade that didn't peak anywhere. It just went really, really high to really, really high intensities, the lower the wavelength got, and it went off to infinity with the lower wavelength. So why didn't we see this when we looked at the spectrum of the sun? It agreed with the predictions at higher wavelengths. It just didn't agree with lower wavelengths. So what somebody named Max Planck did was construct a new theory. This theory, which was called which created the branch called quantum mechanics, speculated that the energy radiated by the black body could exist only in specific numerical or quantum states, where E is equal to some number n, some integer n, so 1, 2, 3, 4, 5, up until however many particles are in the material, times some constant times the frequency. So these were the only allowed frequencies to be set off to be shown by these were the only allowed frequencies, and because there were a finite number of particles in the sun or whatever block body you're looking at, it couldn't reach those high frequency, low wavelengths in the same way. So it died down to zero instead of going up and up in the ultraviolet region. So that is quantum mechanics. Quantum mechanics, quantum means that there are only certain allowed states and that you can count them numerically, or you can count them like 1, 2, 3, 4, 5, instead of it just being a smooth distribution over everything. So that is the definition of the word quantum, and that's where we get the term quantum mechanics. So the photoelectric effect was discovered by Einstein. I think this is actually what he got his Nobel Prize for. And he wasn't a huge proponent of quantum mechanics, but what he did basically set a lot of the foundation for quantum mechanics. I think about as much as blackbody radiation did. But basically what he found was that when you shot radiation, electromagnetic radiation, where just a light at sea of electrons inside a metal, then that's going to knock the electrons out, and they can be picked up by another sensor, which is going to read the kinetic energy of the electrons. So what they found, or what Einstein found, was that the kinetic energy of the electrons was equal to HF, which is the Planck's constant times the frequency of the light that was input, minus BE, where BE is just equal to something called the work function. I don't know why it's called BE in this textbook, but it's called the work function. And what is interesting about this, and what does kind of prove that these are quantum, that light is quantum or quantized, is that each kinetic energy, no matter how much intensity of the electromagnetic state of the electromagnetic light you shine down. So if you shoot a laser with twice as much intensity, with that's twice as bright as an earlier laser, it's still going to come out with the same kinetic energy, which suggests that light, in addition to having the wave property, which we've been talking about, also had a particle property, where the particle property of light comes about as tiny little particles called photons, in the same way that we have particles called electrons or protons or neutrons, where particle just means that it's a discrete thing. We have tiny little particles named photons, and each of those knocks out an electron, and it doesn't matter. And if you were expecting it to be only waves, then what you would see is that as you had more light, as you had a higher intensity of light, more electrons would be knocked out because you were coming at it with more energy. But what we saw is that it's only dependent on the frequency, which means that the energy of light is only in these small little steps from that are dependent only on the frequency. So this is called wave-particle duality. And another example of wave-particle duality comes in momentum from the Compton effect, which is that momentum is conserved in quantum mechanics just as it is in relativity and classical physics. So you have a photon, and if it runs into an electron, then it's going to cause there to be a scattered photon and an electron that has momentum yeah, there's going to be an electron and a scattered photon which have momentum, and then that momentum is going to be conserved. So electrons have conserved discrete momenta and conserved discrete energies, which means that they have particles, particulate properties, as well as the wave properties that we were talking about in earlier lectures. So one of the so photoelectric effect is everywhere. You see it whenever you're trying to talk, or whenever you see like an electronic eye, which is something that measures whether or not you're there by bouncing photons off and seeing if there's a current that's introduced. So if you put your hand into an elevator, then that blocks the beam of photons, which means that there's no current produced, which means that it can tell that somebody's there. Or it can also be used for introducing voltage from the light of the sun in solar powers or solar panels. And then this momentum conservation, this momentum property of light, can be used for something called a solar cell, where you get a really lightweight material, you put it out there, and you catch you catch the photons that are coming from the sun and use that to move your cell by conservation of momentum. So these are just light-based properties. Quantum mechanics changes everything, and Einstein might not have liked it, but he was one of the four founders of it, along with a bunch of other very problematic physicists in the earlier 20th century who led to and quantum mechanics led to the transistor, led to computers, led to all of these different things in addition to just the light the light quantities that we're seeing here, the very direct applications of the photoelectric effect or the Compton effect, which is the effect of energy or photons having momentum. So hopefully that should open your mind up to the possibilities of quantum mechanics, even if we haven't gotten if we didn't go that deeply into it. It is very interesting and very much the basis of anything that you want to do as we go forward in our study of physics.